In this lecture, we will learn design aspects of centrifugal pumps. More precisely, we will learn how to select a centrifugal pump and motor for pumping fluid at a specified rate for a given system. Before going to design part, we will extend the theoretical knowledge gained in first video to more practical sense. We had discussed that energy head developed by backward curve pump decreases linearly with flow. But this is theoretically maximum energy head possible, obtained assuming whole shaft power input got transformed to fluid energy. This is true only for ideal cases. In practice, there will be lots of energy losses associated with pump flow. One of the main energy loss is due to effect of friction in the flow. This loss increases quadratically with velocity. A similar loss occurs when there is sudden expansion or contraction. Magnitude of this is also proportional to velocity square. So, head curve will come down like this. This is the reason why we always try to transform dynamic part of fluid energy to static part in a centrifugal pump. Next is due to recirculation effect in the flow. When flow is below the design flow rate, recirculation losses becomes predominant, as shown in figure. When pump operates at its design flow rate, recirculation loss is almost zero. If there is a difference in blade angle and flow angle, it will cause further loss. Here energy loss happens due to flow impingement and recirculation effect. This is again prominent in off-design flow conditions. So, it tends to have higher losses as we move away from design flow rate point. Energy losses we have discussed so far, which reduce head of the flow, is known as hydraulic loss. So this will be the effective head versus flow rate curve. The shape could be anything like this, depending upon pump parameters. Such curves are known as pump performance curves. Please note that it is quite difficult to determine pump performance curve theoretically, rather they are determined experimentally. Using pump performance curve, one can easily predict what's the pressure rise across the pump by applying energy equation across it. Now, we will see how much power fluid is gaining from pump power input, or shaft power. Power gained by the fluid will be lower than the power supplied. One main factor is hydraulic loss, as we discussed. Other factors are volumetric loss and mechanical loss. So, efficiency of a pump can be defined as power gained by fluid by power supplied to the pump. For a typical centrifugal pump, efficiency will vary like this. Corresponding shaft power variation is as follows. You can note that there is an operating point in pump where efficiency is maximum. It is known as best efficiency point. It is marked on head curve here. For a particular casing, we can fit different sized impellers in it. For a larger impeller, head curve will be like this, and this is the best efficiency point. For impellers of smaller size, head curve will vary like this. Best efficiency points are again marked. So back to the basic question, how to select a centrifugal pump for this application. Main condition is that fluid should be pumped at a particular flow rate to a specified height. Performance characteristics of the system is given in a system curve. That means how pressure drop varies in system with flow rate. Depending upon minor losses and major losses in network, it would vary like this. Please note that system curve will change drastically, depending upon valve opening. Assume this is the system curve, at a particular valve opening. Required flow rate is marked here. The operating point of pump will be intersection point of system curve and pump performance curve. So, depending upon selection of impeller, the pump could operate anywhere here. But we have a requirement of specified flow rate. Out of these operating points, this is the one which is most near to the required flow rate. So, we will select this impeller. In the same graph, we can represent ESO efficiency curves. So, efficiency at the operating condition also can be determined. The required shaft power can be calculated using this equation. This will lead to proper motor selection. This pump will operate well if it can overcome one more problem. A problem of cavitation. We will learn how to design against cavitation in a detailed, separate video.